Hi, Chem 151 students. Welcome back for week 10. This week we're going to be starting to study acid-base equilibria. So we've done a little bit of review coming up to this. I'll kind of review that review to begin with. And that's kind of the beginning of the chapter. And then we'll go into a little bit more detail. We'll talk about weak acids and weak bases in detail. And finally, we'll end up talking about how a salt dissolving or an ionic compound dissolving in a solution can cause it to be acidic or basic. So let's start with the basics here, just the definition of acid base. And here we have a picture of a statue that has been damaged by acid rain. So near the end of the chapter or two, we'll talk about how certain gases can combine with water in the atmosphere and create acidic rainfall, which has damaged many nice art that we've had in the past. And so, let's start to talk about the acid-base concepts to begin with. And what we want to do first is contrast the various definitions of acids. We're going to have three definitions. We'll start with the two most important ones, and then we'll move into talking about the third definition near the end in the third lecture of the week. But the simplest definition of an acid is the Arrhenius definition. So in the Arrhenius definition, an acid is any substance that dissociates in water to produce H plus ions. This happens to actually be exactly the same as the Brønsted-Lowry or the other definition. So we say that an acid, and we'll call just any generic acid, we'll call it HA, where the A is the anion part of the acid. It will separate to make the H plus ion and an anion that goes with that. And so the Arrhenius acid is defined as one that when it dissolves in water, it produces H plus ions. An Arrhenius base is a substance that dissociates in water to produce hydroxide ions directly. So any metal hydroxide, the M here standing for some metal, producing the metal positive ion and a hydroxide negative ion. Now, this is a very strict definition of a base. We have actually now much wider definitions of bases than that. They don't have to be something that dissolves to produce hydroxide directly in water. And so this Arrhenius definition is a kind of old one. The new one, which is called the Brønsted-Lowry definition, is going to include hydroxide and other substances that might serve a similar purpose. So let's move on now to the Brønsted-Lowry definition. So in the Brønsted-Lowry definition, a Brønsted-Lowry acid is one that donates protons or gives H plus ions to another substance. So it's very similar to the Arrhenius definition, the acid. So the Arrhenius definition was that it is a substance that dissociates in water to produce H plus ions. The Brønsted-Lowry definition is one that produces H plus ions and gives them to another substance, for example, water or some other base. And a Brønsted-Lowry base is a substance that accepts a proton, accepts an H plus ion, which are also called protons. It is a proton acceptor. By the way, if you're not used to that terminology, proton, it's because if we have an H atom, it has one electron and one proton. But if you have an H plus 1 ion, it has no electron. That electron is gone. So the electron's not there. All you've got is one proton. And so it's very, very common to call H plus 1 ion a proton. And I will probably call it a proton from now on. H plus ion is very, very commonly called proton. So instead of being hydroxide, which is a substance that hydroxide does accept a proton. So you guys are already aware that if you have H plus and you have hydroxide, if the hydroxide accepts the proton, well, that makes water, right? But hydroxide isn't the only substance that can accept a proton. There are lots of other substances that can accept protons. So in the Brønsted-Lowry definition, this includes all substances that could accept a proton to make something else, not just hydroxide, but a lot of other substances as well. So the Brønsted-Lowry definition is a lot more general, and it's the definition that we generally stick to nowadays. Arrhenius is kind of a historical definition. Brønsted-Lowry is the definition that's most commonly used. An even broader definition is called Lewis acid and base. And we'll discuss that at the end of this chapter. It's one that's not nearly as commonly used all the time as Brønsted-Lowry, because it's even broader and includes a whole other range of compounds. But it is an important definition, and I had a class where the teacher taught everything in terms of, like, basically everything was an acid-base reaction, because we used Lewis acids and bases. It was very interesting. He was a guy that did research on superacids, so he was someone that was always thinking about acid-base chemistry and had a very broad view of it, and that's why he taught the class that way. So generally speaking, the way that we would write this is we would say the H plus, we can write a general acid, which we're going to do a lot here, calling it HA, where the H is the H plus that can be donated. We'll often call a generic base B, and we'll say that it will accept the H plus. So when we have an acid-base reaction, the acid is the H plus donor, so it's going to give the H plus over to the B, and notice what happens to the charges. So the B gets an H plus added, so not only is the H attached now, but the charge goes up by 1 unit, from 0 charge here for the base up to +1 charge, because it got H plus. Basically the H plus leaves behind an electron, and thus that's why what's left here is the HA without the H, but also the charge isn't the same. It goes from 0 down to -1, because when an H plus leaves, it's really leaving an electron behind, and that electron is what causes the negative charge there. And this terminology is going to become exceedingly important to us now, this terminology of conjugate acids and bases. So the conjugate base of an acid is what remains after it has lost an H plus. And so HA, when it loses an H plus, what remains is H minus. So that is the conjugate base of HA. For the base B, what it becomes after it accepts an H plus is this BH plus. So what the base becomes after it accepts an H plus is called the conjugate acid. And this is because when these are weak acid, weak base, there's an equilibrium here. So we can say, well, if this reaction goes in the forward direction, this is the acid, because it is giving the H plus, right? And B is the base because it is accepting the H plus. But if the reaction goes backwards, now going backwards, this BH plus is donating the H plus, right? At this point, if the reaction is going in reverse, so I'll draw this in blue, for the reverse reaction, the H plus is being transferred, from the BH plus over the A minus. And so in the reverse reaction, this is behaving as an acid and giving the H plus. So this conjugate acid of the base is behaving like an acid in the reverse direction. And the A minus is behaving like a base and accepting the H plus and returning to us the HA. And so these are referred to as conjugate acid-base pairs, because A minus is the conjugate base of HA, and HA is the conjugate acid of A minus. It's what you get if an H plus is added. That's called the conjugate acid. B is the conjugate base of BH plus, because it's what you get if the H plus is lost. And so these are called conjugate acid-base pairs, because it depends on the direction that you're looking here. But in general, basically, to make it very simple, for any substance, the conjugate acid, whoops, I shouldn't write that there. The conjugate acid means that you have what you get when you've added 1 H plus. It's a thing that has plus 1 more H plus, right? And the conjugate base is what you have if you have 1 less H plus, so minus 1 H plus. So the conjugate acid of something is what you get if you have an extra H plus. The conjugate base is what you have if you have 1 less H plus. And then if you have a pair like this where so if they differ by 1 H plus, we would call that a conjugate acid-base pair. These differ by a single H plus. These two differ by a single H+, so they're conjugate acid-base pairs. That terminology may or may not have been emphasized in your previous class, but it will be exceedingly important in this class as we move forward. So conjugate acid-base pairs are species who differ by one H+ ion. These differ by one H+ ion. These differ by one H+ ion. Now, it's important also to show this as Lewis structures, because you really get to see what's going on with the electrons when we show this. So here we have an acid. So this is a weak acid. It's going to be a weak acid. That's why we're doing this equilibrium here, meaning it's not going to 100% go to the right. There's going to be some amount of reactant and some amount of product here. So this acid here is giving up its H+. If there's no other base around, there will always be water. So water can behave as the base and accept that proton. So see how water is not a hydroxide, but it can still function as a base because it's functioning as a base by accepting that proton. Now what happens is the H+ leaves, and notice what happens here when it leaves. This bond involves two electrons. When the H+ leaves, both of those electrons are left behind, and they're left behind as a lone pair on this A-. Okay, and so the H+ does not take any electrons with it. That's why this ends up with a negative charge. It has an extra electron now, right here. Now likewise, what happens here is a situation that's similar to what we saw with ligands previously. Remember, ligands made coordinate covalent bonds, meaning that the ligand donated both the electrons that were required to create the bond. This is happening here too. The H+, the water here is making a coordinate covalent bond with the H+. The H+ is popping off right here. It's popping off right here, and then we have the H+ right here, and it has no electrons. What happens is these two electrons right here are going to be donated to create the bond, and you can see that happens right here, right? We have that bond afterwards. I'm going to erase this now, since you can see it on the other side. But what happened was the H+ came off. This too. Came off, it had kept no electrons, it left both of them behind, and then it approached this water, and the water donated both of its electrons to create a bond with the H+. So ultimately, we get a positive ion here, because now this is lacking one electron. And this is referred to as the hydronium ion. And by the way, in terms of just general terminology, if we have an aqueous H+ ion, this is essentially the same thing as saying we have a hydronium ion. Because if an H+ is floating around in water, it's probably stuck to a water molecule like this. So these are often used interchangeably, a proton or a hydronium ion, because if the proton's going to be floating around in water, an aqueous proton, it's going to generally be in the form of a hydronium ion. And so again here we have an acid and the water is the base, it's accepting the proton, and we get the conjugate base of the acid is what you have after it has lost a proton. So it has one less H, and the charge is down by 1 unit from 0 down to -1. And for the water, its conjugate acid is what it is after it has gained 1 H+. So it's one more H, and also the charge is up by 1 unit from 0 up to +1, and that's hydronium ion. Now let's do the same thing with bases. So this was for a weak acid. It donates its proton to water. Same thing when you have a base in water. This time it's not donating a proton, it's accepting a proton. And where it accepts the proton is from water. So when you're writing an equation for a weak base, you have to write in the water. You really have to write it, because the base has to accept a proton from somewhere, and that somewhere is going to be the water, unless there's something else other than water in there. And so just to make a comparison here, we can write HA and water, and the water accepts the proton. But equivalently, just like we're showing here, for acids, we have another option. We can say HA, and we could say H plus and A minus. So, and these are all aqueous. So that's the other way of writing the equation for a weak acid behaving like an acid in water. We don't have to include the water because it's implied that the H plus is associated with water. So we can either write the equation with water and have a hydronium ion like this, HA plus water, hydronium, and A minus, or we could exclude the water and just say we have an aqueous proton. Both of these are completely acceptable. Your book tends towards this second way. I really like this first way because I just think it's easier to write. Both ways are correct. But for weak bases, there are not two ways that you're allowed to write it. There is only one way, because the weak base is accepting a proton, and that proton has to come from somewhere. So you have to write the water to show where the proton's coming from. Again, the proton is going to leave behind both electrons that are in this bond. So these two electrons here, when the proton leaves, they're left behind right here. And the result is that you get this negative hydroxide ion because an extra electron was left behind. So now there's a negative charge. Likewise, the base here is going to make a coordinate covalent bond with the H plus. Both of these electrons are going to be used to create a bond with the H plus, and you can see right there, these two electrons are now in this bond with the H plus. And overall, we're missing one electron. We have a positive 1 charge here because this H plus did not take its electron with it. It left it behind here. So here again, the base is accepting a proton. Its conjugate acid is what you have after it has accepted one H plus. So you can see there's one more H, and the charge is up by 1 unit from 0 up to positive 1. The water has behaved as an acid in this case. And so the water has given up a proton. That's why it's the acid. And when it gives up the proton, it now has one less H, and the charge is down by 1 unit. So this is the conjugate base of water, hydroxide. And again, these are conjugate acid-base pairs. They differ by 1 H plus. These two are conjugate acid-base pairs. They differ by 1 H plus. So I really like showing here the Lewis structure because it shows you how the H plus leaves the electron behind when it leaves. And that causes the conjugate base to be negative if the initial acid was neutral. And then the conjugate acid at the base has a positive charge, assuming the base was neutral. Now, in terms of acid-base strength, so in the past we've said that there's a series of so many acids that are strong and all the rest are weak, right? Or we got so many bases that are strong and all the rest are weak. But in this chapter, what we're going to be focusing on is how strong are the weak acids relative to one another? And why are the ones we call strong acids, why are they so very strong and other ones are weaker? So that's what we're going to talk about here. First of all, here we have a general reaction. Again, this is the way we're going to write general weak acids. So the acid here is behaving as an acid. The water's the base in this case. Because it's going to accept the proton. So this is the same as what we saw earlier. It accepts the proton. We get the H3O plus, which is, if we go backwards, this would be the acid in the reverse direction, right? Because if we go in reverse, then it's losing the H plus. And then this is the conjugate base of this acid. If we were to run this reaction in reverse, this would behave as a base. It would grab a proton, and then you would return to the HA. So when we're thinking about acid strength, what we're really doing is we're comparing the strength of the acid on one side to drive this reaction forward and give up the proton versus the strength of the acid in going in the reverse direction to give the proton back. And the extent to which the reaction will go forward and backwards depends on how strong this acid is compared to this acid. And this base is compared to this base. This is a very strong base. It's going to want to grab a proton and go backwards, right? And so if we had equal concentrations of these reactants and wood products, what direction would the reaction go? Well, it depends on the relative strengths of the acid and the base. The reaction is going to proceed in the direction of going from the stronger acid and base to the weaker acid and base. Because if this acid is stronger than this one, it's going to tend to give up its proton and make this, instead of this base reaccepting the proton and making the acid. So in general, the reaction is going to go from the stronger acid and base to the weaker acid and base. And so what are some ways in which we can evaluate the strength of the acid and the base? Well, we can observe what really is happening, what's happening in the solution. So if we have a very strong acid, we say that that acid 100% dissociates. So what it's going to do is completely separate until there's no H pluses still attached to the A minus. It's going to be all H pluses unattached, making hydronium ions, and there's going to be the anion completely separated from the H plus. So the extent of dissociation is basically 100% for a strong acid. But when it comes to weak acid, we call anything that doesn't 100% dissociate a weak acid, but they are not all equally weak. A weak acid is any acid that only partially dissociates in water, but some dissociate more than others. So for a weak acid, it may partially dissociate, and there'll be a lot of the H plus still attached to the A minus, but some of it will have separated. For a very weak acid, we may have almost no dissociation, and so all of these will remain as the H plus still attached to the A minus. It will not separate. So we'd like to think about, what is a weak acid versus a very weak acid. This distinction of strong acid versus weak acid doesn't tell us a whole lot. What we'd like to know more is how much does it dissociate? How strong is it? Is it very, very strong, or is it kind of strong, or is it, extremely weak like this one? And this is a chart showing the relative strengths of acids. So we have a series of strong acids, the hydrohalic acids, perchloric acid, sulfuric acid, nitric acid. And I discussed this a little bit in lab last week, the 6 strong acids. The other ones that aren't listed here are HBr and HI. Okay. And basically, these are the acids here that we see. These are their conjugate base. So this is what you have after this one has lost an H plus. So when the HClO4 loses an H plus, it makes ClO4 minus. Or when HCl loses its H plus, it has Cl minuses left. And so let's think about this. So if we have HCl and it is 100% dissociating, it is making H plus and Cl minus, and it is not going backwards. Okay, so I'm writing this in the simplistic way without the water. So here we have, this is the acid, and this is its conjugate base. And remember what it means for a base to be a base. What it means is a strong base would be one that wants to really, really grab protons. And a strong acid is an acid that really, really wants to give away its protons and separate from them. So the stronger the acid, the more forward this separation is going to go. What that means is for its conjugate base, it's not going to accept protons back. This reaction does not really go backwards. So the stronger the acid is, the weaker its conjugate base will be, because these are basically opposite situations. If an acid is very strong, that means 100% dissociation. And what that means is that its conjugate base is not going to go and associate back with H pluses very well. So the stronger the acid, the weaker the conjugate base. And so these are very, very strong acids. They're stronger than H3O plus. So now we have a more solid definition of what we call acids. A strong acid. Anything that is a strong acid is an acid that is actually a stronger acid than hydronium. And then anything we call weak acid is a weaker acid than hydronium. And so those include a lot of other acids. But the stronger the acid, the weaker the conjugate base. And then if we have very, very weak acids, what that means is their conjugate bases are very strong. So here, water is a relatively weak acid. Because water is such a weak acid, its conjugate base, hydroxide, is quite strong. It's what we would consider to be the strongest base in water. There are acids that are even weaker. We don't even consider ammonia acid. It's a base. Hydroxide is a terrible acid. So the weaker the acid, the stronger the conjugate base. These are extremely strong bases. They are stronger bases than hydroxide, in fact. So the take-home message here is the stronger the acid, the weaker the conjugate base. And it's also true for bases. The stronger the base, the weaker the conjugate acid. So these are super strong bases. They have very weak conjugate acids. It's because we're talking about opposing situations, right? If this acid is very strong, what that means is this reaction does not go backwards. So of course the conjugate base must be very weak. It's never going to go backwards and pick up a proton. So what are some ways that we could qualitatively evaluate the strength of an acid, or at least understand the relative strengths of acids based on simply the atoms that make them up and their formula? Well, if we have these acids that are binary, so they've only got two elements in them, the H and whatever else they're with. So for acids like these, the way we can evaluate the strength of the acid is based on the size of the anion here. Okay, the bond strength, basically, it's related to the bond strength, because the bigger the anion, like iodide here, is a much bigger anion than fluoride, and the result is that the bond between the H and the I is longer. And so you guys may remember from your previous 150 class, the longer the bond, the easier it is to break. The weaker it is. A longer bond is weaker. You could also think of that like, let's say you're going to karate chop a piece of wood, right? And you want it to be easy. Do you want the piece of wood to be short, or do you want it to be long? Well, if the board is very long, it's easy to karate chop. That's like this right here. The HI, the bond's very long, easy to karate chop. It breaks really easily. So that indicates a very strong acid. The H plus and the I minus can separate very easily. Whereas HF is like trying to karate chop a piece of wood this wide. It's going to be super hard, right? The short bond is harder to break. You can't karate chop it. And so the HF here is the weakest of these acids. And we don't even consider it a strong acid. Although it's for a weak acid, it's pretty strong, but still it's not that strong because this bond is super short, and so it's hard to break. And so the H plus does not come off the F minus very easily. But HI is the strongest out of all these hydrohalic acids. HBr is next, HCl is next. These are all stronger than hydronium. Only HF isn't as strong of an acid as hydronium. And so it is the weakest out of these hydrohalic acids. So basically, the longer the bond in these acids with one bond, the weaker the bond will be, and the stronger the acid will be. Now, that was going vertically on the periodic table. What about horizontally? So horizontally, the strength of the acid depends on the electronegativity of the other atom. The more electronegative the atom is, the more acidic the bond will be. The reason for this is because something you're going to learn more about in organic chemistry is that the more polar a bond is, this HF being the most polar, so this is like super polar bond, super polar, whereas this one's less polar, still pretty polar. This one's like tiny polarity, this one's like no polarity, not polar at all, really, not polar. And so the more polar a bond is, the more likely it is to break. And this is because the electrons are being pulled all to one side, which weakens the bond. And this is why, like hydrocarbons, like plastics, super hard to break bonds. This is why plastics last forever. They're not very polar, they just don't break very easily. So this bond between HF, it's the most polar, it's the easiest to break. this one, water, it's next easiest. Water is not a great, HF is a pretty strong acid. Water is not very strong at all. Ammonia is not an acid at all. It's actually better as a base. And methane is like basically completely unreactive in most cases unless you burn it. And so when it comes to looking at elements horizontally like this, so first we look vertically. If we look horizontally, what will affect the strength of the acid is the polarity of the bond. The HF bond is the most polar, and thus it will be the easiest to break, and this will be the strongest acid, and it will be less strong, very, very rapidly become less strong as we go left on the periodic table. Now for oxoacids, there's two situations. So we have oxoacids are those in which we have the H plus attached to an oxygen atom. That's part of a polyatomic ion. So this is the hypochlorite ion, this is the hypobromide ion, this is the hypoiodide ion. And when it comes to the acid strength here, again, what's going to make an acid strong is a weak bond right here. So to make this an acid, what we need to do is we need this bond to chop right here so that the H plus comes off. And what's going to make this bond easier to chop, again, like the same situation, it's going to be the electronegativity of the atom that's attached to the oxygen. Because what's going to happen is, since this is the most electronegative, it's going to pull electrons in its direction with an effect. The effect is called the inductive effect. And that's going to weaken this bond. And so when this bond is weakened, the H plus more easily pops off and you have a stronger acid. So that is why this hypochlorous acid, hypochlorous acid is going to be a stronger acid than the hypobromous acid, which will be a stronger acid than the hyperiodous acid. And then it will also be a greater inductive effect if there are more oxygen atoms. So for this reason, perchloric acid is considered a strong acid. It's a stronger acid than hydronium. And this is because the more oxygens you have, the greater this inductive effect becomes and the weaker this bond gets. And so the perchloric acid is considered a strong acid. It's stronger than chloric, it's stronger than chlorous acid, which is stronger than hypochlorous acid. And notice that perbromic acid is not considered a strong acid, right? It's the same reason as back here. This is because the bromine is less electronegative. So these oxoacids will be stronger when the non-oxygen atom is more electronegative and when there are more oxygen atoms, because both of those increase the inductive effect, which weakens the bond here and results in easier H plus removal, and thus a stronger acid. So that's how you determine, based on the formula, the relative strength of acids. Finally, of course, we're going to be talking a lot about pH and the pH scale. So you guys should know from previous classes that the pH scale arises due to the dissociation of water. And so we were talking about, going back a few slides here, we called strong acids strong because they were stronger than hydronium. Hydronium is going to be the strongest acid that you can have in water, because if you have any other stronger acid, it's going to 100% dissociate and create hydronium ions anyway. So any acid that is stronger than hydronium is just going to turn into hydronium. If we were rewriting this with the hydronium, it would be HCl plus H2O creates hydronium and Cl minus, right? So, and this would be 100%. So any acid that is stronger than hydronium is going to be 100% make hydronium, and hydronium will be the strongest acid that can be present in water. Likewise, any base that is stronger than hydroxide will react with water to produce hydroxide. And so hydroxide will be the strongest base possible in water. And so essentially, hydronium in water is considered acid, and hydroxide in water is considered acid. And this is because of the so-called leveling effect in water. And that is that water itself can make hydronium and hydroxide, and all these acids and bases are reacting with water in order to produce hydronium and hydroxide as well. And so one water molecule here can give a proton to another, and hydronium is created, and for the acid that lost the H+, hydroxide is created. And of course, hydronium is a conjugate acid of water, which has behaved as the base in this reaction, accepting the proton. And hydroxide is a conjugate base of water, which has this water molecule has behaved as the acid, donating the proton. So there's an equilibrium here. There's an equilibrium, two water molecules being on the left, producing hydronium and hydroxide. And we can write an equilibrium constant for this reaction. And so that equilibrium constant will have product concentrations, hydronium and hydroxide, over reactant concentrations. But water is not aqueous. We don't call water aqueous. It's the bulk liquid. So it's not included in the equilibrium constant. So the Kc for this reaction has a special name. It's called Kw. And its expression is hydronium times hydroxide concentration equals Kw. And because this reaction can always happen in water, every other equilibrium, aqueous equilibrium, is mediated by this reaction. And so it's always going to be the case that the hydronium concentration times the hydroxide concentration is going to be equal to the K of this reaction, also called Kw. So if we're at 25 degrees Celsius, the concentrations of hydronium and hydroxide that are produced are both 1 times 10 to the minus 7 molar, because every time two water molecules react, one hydronium is made and one hydroxide is made. And so if we plug this in now for pure water to get the Kw, we have hydronium times hydroxide concentration. The Kw is 1 times 10 to the minus 14. And I had you guys do some review exercises to kind of get used to using that again. But this is just a reminder of where it comes from. And now that you know about equilibrium, I have a little bit more to say, and that is that just like every other equilibrium constant, the Kw does depend on temperature. So you notice I've stated the temperature here. Kw is different at different temperatures, but at 25 degrees Celsius, it's 1 times 10 to the minus 14. And most of the time, we're going to be working at 25 degrees Celsius, like room temperature. So this formula becomes very useful. You've used it in previous classes. You'll continue to use it in this class. If you have either hydronium or hydroxide concentration, you can get the other one. If we divide both sides by hydroxide, so if we divide both sides by hydroxide, we cancel the hydroxide and we get hydronium. That should divide here. We get hydronium concentration is Kw over hydroxide. So if we have the hydroxide concentration, we can determine the hydronium concentration. Likewise, if we have the hydronium concentration, we can determine the hydroxide concentration. And of course, we would get that just by dividing both sides by hydronium, which would cancel the hydronium, and it would end up on the bottom here. And so this is how we use Kw. And again, I already had you start getting ready for this by practicing what you used it for before. So if we have neutral solution, then both hydronium and hydroxide are 1 times 10 to the minus 7. And this is the mediating effect that we see here. If hydronium concentration increases because we dump in some acid, at the same time, hydroxide concentration must decrease because they always have to multiply to 1 times 10 to the minus 14. Likewise, if we dump a bunch of base in solution, then that is going to cause the hydronium concentration to fall because they must also always multiply to 1 times 10 to the minus 14. And so also as a part of a couple weeks ago, we did pH of household acids and bases. So you get to see the various pHs of these. pH is defined, as you guys know, as the negative log of hydronium concentration. And if we take If we multiply both sides times -1, so we multiply both sides times -1, that cancels this negative. And then we do anti-log. Log is base 10, so to cancel the log, we do 10 to the power. 10 to the power. That's going to cancel our log, and we get hydronium equals anti-log of negative pH. And so I provided you with this formula, even though I didn't explain how to get it. That is how you get it. You guys have your log rules pretty well down, hopefully by now, and so you could determine that yourself. Likewise, there's a value called POH, which is the negative log of hydroxide, and you can do the same thing to get that the hydroxide is the anti-log of negative POH, or 10 to the minus POH. And so a neutral solution here is pH 7, because we saw that the if we have neutral water, for neutral water, the concentration of hydronium equals the concentration of hydroxide, as we saw, and it was 1 times 10 to the minus 7 molar. So if we're getting the pH here, the pH equals the negative log of the hydronium. I can see here, so that would be a negative log for pure water, for a neutral solution, of 1.0 times 10 to the minus 7. And so that is the same as the negative log of 10 to the minus 7. And just a little reminder here, again, log and 10 to the power are opposites of one another, right? So the log cancels the 10 to the power, the negative cancels the negative, and you get 7. Or you could put it into your calculator. And 1 times 10 to the minus 7 is just the same as 10 to the minus 7. So a neutral solution is pH 7. If pH is greater than 7, that's a basic solution. If pH is less than 7, that's acidic. And so you can see the acidity and alkalinity or basicity of a variety of substances. You guys did some antacid analysis here. Milk of magnesia, basic. Stomach acid is around between pH 1 and 2, so it has a concentration of about 1 times 10 to the minus 1 molar of hydrochloric acid. Stomach acid is hydrochloric acid. Human blood is slightly alkaline or slightly basic. It's about 7.35 to 7.45 pH. And so you guys have done some practices of this already. The idea was to kind of get that over with early, so that we can the review over with early, so we can dig right into using these formulas now. I will make a statement now about pH, log rules and significant figures with logs. So I haven't really emphasized it previously, but it becomes really important as we move into this chapter, because you'll often find that you're going to go from concentrations to pH and sometimes back again. And when you do that, if you're not very careful with the sig figs, it can lead to really weird rounding results. So here are the way the log rules work, or the significant figure rules work for logs. If you take the log of a number like this, so here's the question. The hydronium concentration for lemon juice is approximately 0.0025 molar. What is the pH? So the pH is the negative log of the hydronium concentration. What is this? Our hydronium concentration has been stated with 2 sig figs. And so we take the negative log of that. We can use our calculator here. In fact, I want to use the Casio, so I'm going to open that. So if we use the Casio calculator here, we're going to do the negative. Make sure not to hit your minus. Hit the negative. Negative log of 0.0025, and we get about 2.6. And the way we want to write this is, since our molarity 0.0025 had 2 sig figs, we want to write the result so that it has 2 decimal places after. So our result with the proper number of sig figs would be 2.60. And likewise, if we go backwards and get the hydronium concentration, so if we go backwards and get the hydronium concentration is the antilog of the negative pH. And so this is going to be the antilog of negative 2.60. Okay. And so we would, to do that, on your calculator, you can type 10 to the power, but it's cleaner to do shift and then log, which will do the antilog, and then the negative 2.6. And we'll get 0.0025. And the reason why we need this extra 0 is because there was always a little wiggle room in the last sig fig. This 6 isn't the last sig fig. You'll notice it because if I change it to 2.7, it's going to totally throw this thing off. So I'll show you. Antilog negative 2.7. Now it's totally different, right? It's 0.0019. That is not within the right range of being 0.0025. So that's why it's appropriate to do one more sig fig, because if I do antilog negative 2.61 now, where 1 is actually the last sig fig, I get something that's still reasonable. It still rounds to 0.0025. And this is why it's important to pay attention to these sig fig rules now. And so I did give you a summary of kind of like explanation of this on Canvas. And it includes several examples right here for why this is. So it gives you the rules. When you take the log of a number with n significant figures, the result should have n decimal places. So just like we saw here, 2 sig figs, 2 decimal places. And it does logs for a variety of these. So you can see that if I change the last sig fig here, where my sig fig is shifting is 2 after the decimal, actually. That's the last sig fig on that one. So it's appropriate to go to 2 after the sig figs. Likewise, if you go in the opposite way, when doing the antilog of something with n decimal places, the result should have n sig figs. So you'll notice that this one has 3 decimal places after it. And when I shift the third after the decimal, my number shifts at the 3rd sig fig, right? So that's where the last sig fig is, actually at the 3rd sig fig, when I'm moving 3 after the decimal. And so the rules are given to you here in the boxes. They're also here on the slide. So if you're taking the log of a number with 2 sig figs, the result should have 2 decimal places. If you're taking the antilog of a number with 2 decimal places, you should write the result with 2 sig figs. And that's the rules for sig figs for using for logs. And it wasn't as important previously, but it becomes more and more important in this chapter. So I wanted to make sure to mention it because it will help you avoid a lot of confusion when you're going back and forth between logs like you do in this chapter. And so here's another question. Calculate the pH of an ammonia solution that has hydroxide concentration 0.0019. There's a couple different ways you can do this. You've already done some practice with that. But I do want to point out that you can't just take the negative log of this and get the pH because it's the hydroxide concentration. So what you can do is you can find the hydronium concentration first, or you can get the POH. But if we plug this in here for the hydroxide concentration, we'd get 1 times 10 to the minus 14, over 0.019, 1 EE minus 14, divide by 0.0019. And so, I think I need to put this back in scientific notation. There we go. So we get 5.3 times 10 to the minus 12 molar. And don't forget the molarities when you're doing concentrations there. So that's the hydronium concentration. If we want the pH now, we take the negative log of that. pH is negative log of that. So we'd say negative log 5.3 E minus 12, and we get 11.28. And now again, this has two sig figs, right? So we're going to write the result of 2 after the decimal. So we write 11.27, but we round up the 7 because there's a 5 next to it. So we write 11.28. Again, this is a big difference. If you write down 11, you're going to lose a lot. And if you try to go backwards, you're going to get a result that's very different. And that's why I'm urging you to pay attention to these log sig fig rules now, so you avoid that confusion. Okay. Finally, so you guys did some of this before too. So it says acid rain is serious, right? Fish will die in pH lower than 4.5. Calculate the hydronium concentration in a lake that has pH 4.5. Hydronium concentration is the antilog of the negative pH. So we do antilog of negative 4.5. And I'm mostly demonstrating the log rules here with these. So when we're doing the antilogs, we'll do second log here of negative 4.5. Okay, so when we were taking the log, we write a result that has as many decimal places as we have sig figs. Now here we're doing the antilog. We're going to write a result with as many sig figs as we have decimal places. We only have one decimal place. Place after the decimal. So we're going to write the result with 1 sig fig. So we're going to write 3 times 10 to the minus 5 molar. That's appropriate here because we write our result with as many sig figs as we have places after the decimal in our antilog. We don't really know any more than those. Another thing we've been talking about here is acid-base indicators. So you guys have actually begun to use some acid-base indicators, and what you saw, some of you will be doing this tomorrow actually still, is you saw the result of an acid-base indicator, phenolphthalein, changing color over a specific pH range. And that's what acid-base indicators do. And depending on which reaction you're doing, it's going to have a different range of pHs that it's going to have. You'll notice this as you were doing experiment 10. The indicator phenolphthalein was okay for a couple of your reactions that you were doing, but it wasn't okay for some of the other ones because they were not passing that pH range. And the way an acid-base indicator works is that you've got an acid-base indicator will be an acid and its conjugate base in solution. And when this acid reacts with enough base, let's say, it will create the conjugate base, and the conjugate base will have a different color than the acid. And that's why these work well as acid-base indicators, because the acid and its conjugate base that compose the acid-base indicator have different colors. And so depending on the pH, you will have either the acid, which has one color, or the conjugate base, which has another. If you are increasing the pH past a certain point, you'll have the conjugate base, which will be a color. If you are decreasing the pH and making more acidic, the reaction will shift this way, and you will get more of this reactant, and the color will be color A. And the pH at which this shift, either left or right, happens depends on the particular acid and conjugate base that you're using as the indicator. And so the one you used in the titration, or will use if you're having it on Tuesday, is a phenolphthalein, which changes from colorless at lower pHs, and then around between 8 and 10 it changes to red. So for many of you, you're doing a titration that it just barely got to pH 9, so it was just barely starting to change color, whereas some of your other titrations, they stopped way here at pH 13, so the color change was quite dramatic. And so when we're doing these reactions, our titrations, we're going to want to choose an indicator that will change color in the pH range that is changing in our reaction. So if in our reaction the pH is changing rapidly from 3 to 7, well, then a good indicator might be bromocresol green or methyl orange, but these indicators would not be so great. Or in the course of your reaction, if it's changing from pH 8 to pH 12, well, maybe these two indicators would be good for that. And so you're going to want to choose an indicator that changes color in the pH range over which your reaction is changing color, or is occurring rather. And that will depend on the acids and the bases that are involved in your reaction. And we'll go more into that as we move forward. But that's the way that these acid-base indicators function. Finally, you should, from previous classes, know how to calculate the pH of strong acids or bases. We did some review on this, so we did problems like this previously. If we have HNO3 at a concentration of 0.025, this is a strong acid, so it 100% dissociates. So that means whatever concentration of HNO3 you had, you're going to have that concentration of hydronium. So the hydronium concentration will be equal to what the nitric acid concentration was, because one of these dissociates, makes one of these, and so our concentration is the same. So the pH will be the negative log of that concentration, or the negative log of 0.025. Again, you should be able to plug that in now. I didn't have too many questions, I think, on that exercise, but if you want to go back to that and you still have questions, it's fine to ask me now that we're really getting into this material. Notice again, we're taking the log of a number with 2 sig figs, so we round our result so that it's 2 after the decimal, 1.60. The pH of a strong base, again, these are our strong bases here. We discussed them as well in lab, or we'll do so if you have the lab on Tuesday. So what is the pH of a 0.025 molar solution of sodium hydroxide? Again, sodium hydroxide completely dissociates, so your concentration 0.025 molar sodium hydroxide, that is equal to your concentration of hydroxide. And we need to get the hydronium concentration to get the pH, so we use our handy Kw formula. The Kw divided by hydroxide, we plug in the concentration for the hydroxide, and we get 1 times 10 to the minus 14 divided by 0.025. That's going to be 4 times 10 to the minus 13, and we will write this with 2 sig figs. So 4.0 times 10 to the minus 13. Then to get the pH, we take the negative log of that concentration. So negative log 4.0 times 10 to the minus 13 equals, and that's 12.39, or if we round up here because it's 12.40. And again, notice we're taking the log of a number with 2 sig figs, so we write the result to 2 after the decimal. So we write 12.40. That is the correct number of sig figs for that. So these problems should be familiar. We've done some already, and you did some in your last class, but this is the way you handle the sig figs. In our next lecture, we're going to start to talk about equilibria for weak acids and weak bases. So up till now, we've just focused on some of the review and how to determine which acids are stronger than others, but we haven't really gotten into how much a weak acid dissociates. So strong acids dissociate 100%, weak acids and bases less so. So how much so? That's going to be given by for acids by what's called the acid dissociation constant, or Ka. And as we move into the next lecture, we'll be talking about Ka and how to use that to determine the equilibrium concentrations of hydronium and the pH. I'll see you in the next one.